The optimal receiver for an AWGN channel uses map detection rule. Now we will look at the implementation of this optimal receiver for the AWGN channels. We have studied one form of map detection rule which is given here, and where Cj is the bias term. Now this can be easily implemented as shown in this figure. This basically corresponds to the correlation. The received signal basically gets correlated with S1t, here it gets correlated with S2t and SMT, correct? And then to this outputs you add the bias terms and select the largest value and decide the message transmitted. Now because of this block out here, which is cross correlation between the signal xt and sjt, this is known as a correlation receiver, and since there are m number of signals corresponding to m number of messages, we have m correlators out here. We have also studied another form of map detection rule in ANWGN channel, and it is given by this expression. Here your vector x is dependent on the received signal. So any element of this vector, say xj, is obtained by taking the projection of the received signal xt onto phi j. Now to implement this, we will first have to get this vector x and then take the dot product with sj, and this can be implemented using the block schematic diagram receiver as shown in this figure. So this gives you the projection of xt on different basis signals. You get your vector x, each of this vector gets correlated, or you take the dot product with m copies of the m vectors corresponding to m message signals, and then you add the bias terms and select the largest output. Again this basically this is known as correlation receiver because of cross correlating xt with different phi j's and integrating it. And here you require n number of correlators corresponding to n basis signals. Now it might appear that this is more complex than the earlier block diagram, but in a practical situations this may turn out to be easier to implement because the value of n would be much lesser than m, and then in that case you will require only n correlators, whereas here you require m correlators. Now both these correlation receivers can also be implemented using what is known as match filter. So we will study now the concept of match filter. In both the correlation receiver implementation which we just saw, we compute quantities of the form xt multiplied by zt. Let me call this as xz, and zt could be either sjt or it could be phi jt. So, let us define a filter with an impulse response Ht and let it be equal to z of t minus t. Then this filter is called a match filter because it is a filter which is matched to the signal Zt using this relationship. So, now let us assume that you have the input xt to this filter ht. So, let us compute the output for this. Yt is equal to convolution of xt with ht. This is equal to substituting the value for ht Now, if you evaluate this output Yt at t equal to capital T, then we get Yt is equal to x tau z tau d tau, which is xz which we had defined earlier. So, in other words, the output of the correlator xz can be obtained by sampling the output of the match filter at time t equal to capital T. Note that this sampling has to be done exactly at t equal to capital T, where this capital T is the arbitrary value used in the design of the match filter. Now, as long as this condition is satisfied, the choice of capital T is irrelevant. However, from a practical point of view, T has to be selected in such a way that the resulting filters are causal. So, what we mean that we must have Ht should be equal to 0 for t less than 0. This puts a practical limit on possible values of capital T. And so, using this concept, a match filter implementation of the optimal receiver which we had studied earlier, let us see that how does it look. So, if we use for Zt to be equal to St, correct, then this is the match filter receiver which I get, and this is equivalent to the correlation receiver with m correlators, correct. So, this filter can be implemented using the match filter. So, in place of these two blocks, they have been substituted by just one single filters, correct. So, similarly, we could implement the match filter for this case. So, we can substitute these two blocks by its match filter. So, Zt gets substituted by phi jt, and if we do that, we get this block. It is important. Now, these are known as match filter with n filters because corresponding to n basis signals, and this have to be sampled at exactly t equal to capital T. If we do that kind of a sampling, then the output from all the 4 receivers which we have seen will be same. Okay? Fine. Now, let us look at some of the properties of this match filters. So, we look at the frequency domain properties of the match filter. So, in our case what we will do is we will choose ZT to be ST. So, your match filter now HT is going to be ST minus capital T minus small t. Your ST could be one of your message signal. So, it could be either S1T, S23 or up to SMT, any one of this. Okay. So, now take the Fourier transform of this. If you take the Fourier transform, we get this equal to so the match filter has a frequency response that is the complex conjugate of the transmitted signal spectrum. So, this has spectrum which is given by SF, correct. So, this match filter frequency response is the complex conjugated of the transmitted signal spectrum multiplied by the phase factor e raised to minus j 2 pi f t, which represents the sampling delay of capital T. So, in other words, the magnitude response of the match filter is identical to the magnitude response of the signal ST, and the phase of HF is the negative of the phase of SF shifted by 2 pi ft. Okay. Another interesting property of the match filter is the signal to noise maximizing property. So, let us assume that we have a signal xt which is equal to desired signal st plus noise nt, and this signal xt is passed through a filter with an impulse response say ht to get the output yt. So, your yt will be equal to xt convol with ht. This will give me st convol with ht plus noise convol with ht. Now, I call this component of the due to the signal as yst in the output, and this is the component due to the noise. So, let me call it as nu t. We assume that this noise nt is a zero mean Gaussian process. So, this your nu t is also going to be Gaussian process. We also assume that this is a white noise. So, then obviously this will not be a white noise, but still it will be a Gaussian. It will satisfy the Gaussian characteristic. Okay. So, now the Fourier transform of your output component corresponding to the signal basically is equal to HF multiplied by SF. So, this is the output due to the signal part, and noise is nu t. So, if you want to compute the output due to the signal part, we could use the inverse Fourier transform of this, and if we do that, we would get it as follows. And if the signal is sampled at t equal to capital T, then I would get the output to be equal to this expression. And as far as the noise is concerned, the output noise will have 0 mean, because we are assuming that the input noise has 0 mean, and it will have variance which will be given by this expression. So, variance of my noise is going to be, power spectral density is going to be squared multiplied by input power spectral density, and I have to integrate this over the frequency range. So, this is the value which I will get. This is equal to nothing but italic n by 2. I am assuming white noise, and EH, where EH is the energy in the impulse response HT. So, now with this, let us define the signal to noise ratio at the output of the filter HF to be this quantity. Output signal squared divided by the variance of the noise that is nu t. Now, we know from the Cauchy-Schwarz inequality for finite energy complex valued function x omega and y omega is given by this expression, correct, and this is equal only if y omega is some constant, arbitrary constant multiplied by x conjugate omega. So, if we use this relationship, then we can write this ys square t, which is equal to HF SF e raised to j 2 pi ft df squared. Now, this will be always less than or equal to this quantity by Cauchy-Schwarz inequality. So, this is equal to energy in impulse response HT, this is the energy in ST, and this will be equal only if HF is equal to of the form some constant alpha multiplied by x conjugate e raised to minus j 2 pi ft. So, from this we get signal to noise ratio at the output of the match filter, which is equal to this quantity always less than or equal to So, this comes out to be twice Es by italic n. Okay. So, what this shows that the filter HF that maximizes the signal to noise ratio at output must satisfy the relationship HF is equal to this, correct. So, we could choose alpha equal to 1, correct. So, and the maximum value which we can get is 2 Es by italic n. Okay. So, quickly to appreciate what we have done, let us take one example. So, let us say I have two signals S1t and S2t. Right. Now, looking at this signal, it is very easy to see what are the orthogonal basis signal to represent these two signals. They will be similar signals except for the normalizing factor. So, what I will get is here phi 1t will be equal to this signal and phi 2t will be equal to this signal, which is similar to this signal except for the heights. Okay, fine. Having done this, if you were required to implement this using the match filter implementation given by this block diagram, in our case here now n will be equal to 2. So, I will get x1 and x2. So, I need to compute phi 1 capital T minus T and phi 2 capital T minus T, fine. So, if you do this basically, so this is this, and from here I can get my H1t simple is this, and looking at this figure also it is very simple. Look here, my phi 1t and phi 2t are this. Phi 1 capital T minus T means I first reflect my phi 1 about y axis, that means I take the mirror image and then shift that by capital T to get my H1t. So, here I take the mirror image and shift it by capital T. If I do it, basically I will get this quantity as my H1t. And similarly here I reflect it about this point and then shift it by capital T, I will get this for my H2t. Okay. So, I have my two filters and now we need to compute x1 and x2. So, let me assume for this case that I have transmitted my signal S1t. So, if I transmit my signal S1t, the outputs from the two filters are going to be S1t multiplied by H1t. The other match filter output will be S1t multiplied by H2t. At the receiver basically we receive along with this signal S1t the noise also, correct. So, we will look at the noise component later on. We are just looking at what happens at the output with the signal components. Let me denote y1t and y2t the outputs this and sample them at t equal to capital T. These are the values which I sample them. Now, it is very simple to see that this is going to be output at capital T and this is going to be output from the other filter at capital T. Graphically the outputs have been shown here. If you have to convolve this with this. So, if you convolve with this, you will start getting output only from 0.5 T, capital T. It will go to the maximum value and decrease. Same input has to be applied to this filter H2T. If you do this basically you will start getting the output like this. Now, you sample this both this output at T equal to capital T. If I do this basically, so from the first channel I will get this value and from the second channel I will get this value corresponding to the signal component of the output. Okay, fine. So, your receive vector, what we are saying is this vector x1, x2, that will be your receive vector. So, that is simple. I denote it x1, x2. So, at t will be equal to, so the first one I will have the signal component, and this value you see here basically when this and this coincides, the maximum value here is going to be given by what I have written out here. It is a multiplied by root of 2 by t, which is equivalent to root of half a squared t, correct? Fine. Okay. So, I will get, and this is equal to the signal energy. This is exactly equal to signal energy in this a squared square root of that, sorry, this will be the square root of the signal energy at this point. Okay. So, I get the square root of the signal energy, plus there will be a noise component, and the second x2 one, as far as the signal is concerned, it is 0 because we have sampled at t equal to capital T. So, there is only noise component, so I call it as N2. So, this is the noise component y1 nt, this y2 nt, N2 noise component. Okay. And what are these noise components? How do I get them? Simple. My nt is getting projected on the basis signals. You have two basis signals, phi 1 and phi 2. So, I will get y1n sampled at t equal to t, y2n sampled at t equal to t by evaluating this. Fine. Now, obviously, it is very simple to see here because we are assuming it to be 0 mean noise process. This is 0. Variance, again, it is going to be the integration of the power spectral density. Output power spectral density is this squared, HF filter squared, multiplied by input power spectral density. We are assuming it to be white noise. So, it is italic n by 2, and then you have to integrate that over the all frequencies. If you do this, basically this is equal to eta by 2. Remember, this quantity out here is the same as, because we are assuming this filter HF is equal to this filter or this filter. So, this is the energy basically in the filter. You could use directly in the frequency domain or you could compute in the time domain. We know that energy of the orthonormal signals are going to be 1, and that is how you get this to be equal to 1. This is italic n by 2, and so if you calculate the signal to noise ratio at the output for the first match filter, you will get the signal component which is equal to root Es squared, that is same as Yst squared, and the noise variance which is equal to this. So, if you take the ratio, I get this quantity, which is the same quantity which we derive for the match filter. So, we have said that the maximum value of the output of the match filter as far as the signal to noise ratio is concerned is twice multiplied by the energy of the signal divided by italic n. So, this agrees with what we have derived earlier for the maximum value of signal to noise ratio at the output of the match filter when sampled at t equal to capital T. Okay. Now, in our study of Emery communication, we have designed the optimal receiver. Now, what is required is basically we are supposed to also analyze the performance of this receiver in terms of error probability, and to do that basically we will require to understand the concept of decision regions in the signal space, and then using that concept we will have to evaluate the probability of error of a particular receiver, and this we will do next. Thank you.